This lecture today is about climate responsive design. My name is Thomas Auer. I'm director at TransSolar, an engineering company in Stuttgart, Munich, New York, and Paris, and professor at TU Munich. So this is the challenge of our time. We need to decarbonize our building sector, and the question is, how can we achieve that? This is what we see a lot. People place gadgets on something which is stupid to begin with. And we have to think about the thing. We have to think about becoming efficient by design and not by applying gadgets. Let me show you one example, a project we worked on with TransSolar already something like almost 15 years ago. It's the headquarters of Manitoba Hydro in Winnipeg in Canada. As a starting point of climate responsive design, we need to understand the local climate condition. So this is an example of downtown Winnipeg. It can become as cold as minus 35 degrees. And when you throw boiling water into the air, it freezes instantaneously. But those conditions you see here are very typical. It can become very cold, but whenever it's really cold, it's always sunny. So we also looked at how much solar radiation do we have in Winnipeg. And we saw that on a horizontal surface, there's more solar radiation than any location we have in Germany. It's more than the city of Milan. It's almost as much as the city of Rome in Italy. And it's a lot of, in wintertime, we looked at how much solar exposure do we have on a vertical south facade. And it was a surprise that we found more solar exposure on a vertical south facade when we have low sun angles in winter than we have in summer. So it became pretty obvious that let's say, passive solar design has opportunities and a big potential in this climate conditions. So we ended up with this kind of adaptive building structure where we have lots of buffer zones where we absorb solar energy. So this is a south-facing atria. The building is an 18-story tower on a 6-story podium where 2,000 employees of Manitoba Hydro work. And in these 6-story atrias, we absorb solar energy, we supply fresh air into it, we humidify by this water feature you see in the background, and then we take the air heated up by the sun and distribute it on the left side into the building, into the depth of the floor plate. There are units behind those panels on the left side, and the main supply air units are integrated in this bench you see on the right side. In summer, we open it up so that it becomes basically like an outdoor terrace. And then to the east and to the west, we do have a double facade with a shading device in between so that we control sun exposure and solar transmission outside the conditioned environment. We do have radiant heating and cooling integrated in the concrete structure, in the concrete slab. The mechanical system is providing displacement ventilation from below, but we do have these adaptive facade systems with buffer zones that react to the changing climate conditions that occur during the course of the year, during the course of the day. So what does it mean? We do have daylight exposure on all workplaces. We do have natural ventilation on all workplaces. We do have 100% fresh air supply on all workplaces and all these kind of things. And so what we recognized is, first of all, after 3 years of operation, compared to other buildings, which are fully air conditioned, we have only half as many complaints in this building. And we have 1.25 less sick days compared to the other facilities operated by Manitoba Hydro. This is significant. Also, when we think about costs, when we think about budget, these 1.25 days applied or multiplied by 2,000 employees working in this building is worthwhile something between $2 and $3 million per year. And this was the energy balance. So CBIP was the, MNECB here was the code requirement when we designed the building, something like 250-ish kilowatt hours per square meter a year. And our projection, our modeling in design showed something like 90 kilowatt hours per year. So you see that we significantly reduced energy consumption or efficiency of the building. We also have a geothermal system under the building with almost 300 boreholes, providing 100% cooling for the building and 50% of the heating demand in combination with the heat pump. So there are also included a couple of technical innovations into the building design, hybridized into the building design. And then we also monitored the building and supported adjusting the systems over a period of 2 years. And the first year when we had a full set of data was September of 2010. And then you see here, we exceeded the energy consumption by almost 100% in the first year of operation. Then in October of 2010, the November of 2010, December of 2010, and so on, you see how we, let's say, incrementally improved building operation. We had some hydronic issues, which got fixed here, so that there you see a big jump, but it took us overall 2 years until we reached and even become better than what we projected in design with our computer modeling. So this was another surprise, let's say, that it really took us 2 years to get to, let's say, correct an operation as designed, and that we reached the projected numbers projected in design. So what did we do wrong? So we started to look into this. We started to look into, let's say, this what we call performance gap issue, if it happens only to us or happens only also to others. And we found this study from the Royal Institute of British Architects, which is called Better Spaces for Learning. And they looked at almost 60,000 schools all over Europe and found out that 95% of these buildings did not perform as designed. And then we found a study of TU Braunschweig where they said that in average, office buildings they looked at had a 70% higher energy consumption as projected in design. 70%. That's the average performance gap in these office buildings. So what we showed with Manitoba Hydro is that we can have these buildings, highly glazed buildings, even in a harsh and extreme climate of temperature differences between winter and summer of 70 degrees with strong winds, etc., etc. And we can achieve high energy performance, we can achieve high environmental quality, but we see a level of complexity which leads to high performance gaps. And the question is, can we do better? Can we come up with a model that's more easy to apply? And at TU Munich, we published those 2 books. In the first book, together with Florian Nagler, we looked at 12 schools, which we started to compare. And in the second book, we put together with Hermann Kaufmann, we looked at non-residential buildings built out of rammed earth, of clay and timber. And so the first book, we looked at schools, 12 schools from different decades. And the first one is on the upper left side, which is designed by Theodor Fischer, and it got completed in 1898. So more than 120 years ago. And then you find buildings from all different periods. And on the bottom right side, there's a building from Florian Nagler and Hermann Kaufmann, which is a school built out of timber, which won the German Timber Award, etc., etc. If here you see pictures from the classrooms, and there's something specific you see on the upper left side. The school of Theodor Fischer the classroom is bigger. It has 80 square meters instead of 60. It has a 4-meter floor to ceiling height instead of 3 meters. And this makes a difference. So we started to measure indoor air quality, thermal comfort, acoustics, daylight. Here you see again a section as well as a picture from the inside of the Theodor Fischer building. And the surprise was what we figured out in terms of thermal comfort in summer, overheating. Among all schools without mechanical cooling, the Theodor Fischer School performed the best. In terms of air quality, among all schools without mechanical ventilation, which were naturally ventilated, the Theodor Fischer School performed the best. With the lowest fenestration ratio, we achieved the most even and best distribution of daylight due to the fact that the windows are very tall and daylight goes very deep into the classroom. We get a very even daylight utilization on a very good level. And even on acoustic, in terms of acoustics, there is no acoustical measure, there is no absorbing surfaces attached to the building structure, to the walls or ceiling. The only thing they have is for daylight control, they have these very big curtains, like a heavy curtain, and it's so much fabric because the space is so tall that even the acoustical absorption works really well, and we have really good reverberation times and a very good acoustic in this classroom. So from all factors, the Theodor Fischer School was always among the best, and even in looking at energy, they now, after 120 years, they replace the window, bring in high state-of-the-art glazing. They insulate against the attic, they insulate the bottom floor plate. If they do after this renovation, the energy performance is something like 30% lower compared to the Florian Nagler and Hermann Kaufmann School. But then looking at the mechanical room, you see here, that's the mechanical room of the Theodor Fischer School, which is basically a boiler room of something like 20-ish square meter or 30. And you see that the Florian Nagler Hermann Kaufmann School, they needed to build a whole gym under the building to house all the mechanical equipment. The mechanical equipment that is used to optimize energy performance, energy efficiency, that is also used to provide good air quality, and so on. But what we see is the lack of volume. The only reason the Theodor Fischer building behaves much better is a lot of thermal mass, thick walls, and the fact that it's taller and more spacious. We have almost twice as much air per kid sitting in this classroom compared to, let's say, for instance, the Diedorf School of Florian Nagler. And then let's say we replace this function, this natural function, with mechanical systems, so that it's really questionable that it works that well at the end of the day. And as a matter of fact, it took the school almost 3 years to get to a proper operation. So we need to become more robust. I think that was the conclusion. And based on this knowledge and based onto this philosophy, we started to work with Haas Cook Zemrig Architects on the Alnatura campus in Darmstadt. And pretty soon we concluded that we should use rammed earth as a material. And Lehmton Erde, a company from Austria, they brought their machinery on site to prefab these rammed earth wall panels, which are something like 70-ish centimeter thick with, let's say, this insulation, this mineral insulation integrated into the wall. And so those are the prefab panels. You also see that there is heating and cooling piping integrated into these wall panels, and then finally brought it on site. So those panels were manufactured like 50 meters off site and then brought with a cherry picker on site, being installed into the building. Here you see a couple of images, and we did measurements which we published in this second book I mentioned. And I just want to point out, I'm not going through all the measurements in detail. I just want to point out the level of humidity control we achieve with this thick, let's say, clay walls, rammed earth walls. You see the red is outside, the green and the blue is inside. You see, if we always stay within the gray band, in summer We take off the peaks when it's super muggy and humid outside. The same in winter when it becomes really dry outside. The material, the hygroscopic potential of the material very well provides comfort inside. So it's not only the thermal mass, it's also the hygroscopic mass, which supports the building operation, which provides a passive support and leads to this very comfortable conditions on the inside. So there's always now the question of how much material can we justify. So thinking of Theodor Fischer having the thick wall, thinking of Alnatura with the thick wall. So here you see the kilograms material used for 1 square meter of wall on the right side. And here at the bottom, you see the double facade, for instance, of Manitoba Hydro. It's the least amount of material, whereas, let's say, a rammed earth wall with wood fiber insulation is the highest amount of material one can use. If we look at embodied carbon, we see the opposite. We see that there is the glass, the double facade, has the highest amount of embodied carbon, more than a concrete wall with styrofoam insulation. Let's say embodied carbon only for phase A for construction, whereas the rammed earth wall insulated with wood fiber has a negative footprint, the same as we see for a solid wood combined with wood fiber insulation wall. So there is no correlation between kilogram material use and embodied carbon. It's about what kind of material we use to really achieve this level of quality, this level of design. And then looking at extreme climates, finally looking at the NUS building, the school, the architecture school at the National University of Singapore, designed by Series Multiply, our Munich office, Wolfgang Kessling, worked on the design for this building. And in Singapore, this very tropical and humid climate, there was this question, is it possible to achieve a net zero energy building in these extreme conditions? You already see this in a section, this extended roof structure to maximize the roof surface to be covered with solar panels to maximize renewable energy generation. But the question is, how can we minimize demand? And then the proposal was to come with to propose an adaptive comfort approach, not designing the building to 22 degrees, not designing the building to become a refrigerator, rather to provide tempered air and elevated airspeed at a higher temperature. So ceiling fans was the solution. Here you see a section again with the different conditions in the various zones. And then when you look at comfort, so this is the comfort tool, the online comfort tool of the University of Berkeley, UC Berkeley. And you see that if you put in 29 degrees C as an air temperature and as a mean radiant temperature without elevated airspeed, you're way outside comfort zone. But if you have an elevated airspeed of just 0.7 meters per second, which is not that much, ASHRAE allows up to 1.2 meters per second, you see that you can shift the comfort zone and you get at 29 degrees and slightly increased humidity, you get into the comfort zone. And so those were all the boundary conditions for the modeling. And if we look at the modeling, we see that a reference building, 500 megawatt hours per year is the budget, is what we can produce on the roof of the building. A reference building would use 4 times as much. If we optimize the envelope, we are here. If we have the highest efficient AC system we can think of, we might come up here. But through the hybrid system and then some, let's say, iterations in design optimization on the envelope, on the schedules, etc., we manage, or the Munich office, Wolfgang Kessling, managed that we designed the building to get into the budget, the available budget, to achieve zero energy carbon, to achieve net zero energy use for this building in this tropical climate. So let me finish with this picture we took from a magazine where they said, "Welcome to the breathtaking Tokyo Water Park." And then they said where you can wash away the pressure and stress of the overcrowded city. So this is a little funny when we compare it to this picture. However, what it shows us is that, let's say, the energy consumption in this facility per user, per person using it, is negligible. So it shows us that, let's say, we can't separate energy efficiency, carbon emissions, embodied carbon from environmental and architectural quality. We have to see it as integral to the architecture approach. We have to provide spaces and buildings people love, people like, so that they really use it and enjoy it. And coming back to this example of Singapore, designing a refrigerator where people freeze to death, where people have to wear a pullover in summer, that doesn't make any sense. That's not sustainable. That's not healthy. So we have to bring all these aspects together in a climate responsive approach. Thank you very much.